Okay, so let's continue with some examples. You will see actually application is kind of easy if you remember the form of the PDFs. Okay, so let's see an example here. Let's say exponential distributed, negative exponential or 1 over theta. So it's given to us, and we have a random sample of size and for that. And prior distribution about the unknown parameter theta is given as gamma with parameters alpha and 1 over beta. Okay, so this is the prior distribution. It's already given to us, and at the beginning of our experiment we know everything about this. So theta distributed as gamma with these parameters, and then we collect a sample, and it is exponential distributed. And now we want to find the posterior distribution. Okay, so what is the posterior distribution? So this is unknown. Okay, so first of all, let's start with the classical approach case. So we know that our PDF for x is this one. And theta is unknown, and we use the minimum variance unbiased estimator approach to be able to estimate the unknown parameter theta. X is greater than 0, theta greater than 0, but in this approach theta is unknown, but it's fixed quantity. So we know that expected x for this case is 1 over theta, and variance of x is 1 over theta squared, and we know that MLE of theta, which is theta hat, is 1 over x bar or n over y, let's say. Okay, so let's see what we will obtain as the posterior distribution of theta. So let's find the likelihood function of x sample x1 to xn given parameter value, which is theta to the n e to the minus theta summation xi, each xi is greater than 0, theta greater than 0. So this is our likelihood function. Our summation xi is the statistic here that we have. It's also positive, and we know it's given that prior distribution of theta is alpha and 1 over beta. Okay, so let's write the gamma PDF with these parameters, but right now this is a distribution of theta, so we have to replace x by theta. Okay, so be careful about that. So theta beta. Okay, and theta is positive, beta alpha, so these are also positive quantities, and we know that from here expected theta is the multiplication of the parameters, which is this one, and variance of theta alpha over 1 over beta square. So this is a property of gamma distribution, you know. Okay, so let's find the posterior distribution. So let's say we have this prior and we collect our sample, which is exponential distribution. Then after combining these information, then our posterior distribution will be proportional to the likelihood function given theta and posterior. Okay, so all you have to do is multiply the likelihood function by the prior distribution, but we have proportional to. Okay, so be careful about that. So we have to so this will be a function of theta, so theta will be our random variable here. Okay, then you have to recognize the parameters, unknown parameters, and look at the form of the PDF. It is a known type of PDF or not. If it is not known PDF, then you have to calculate the denominator part, you know, which is the same quantity, likelihood times the prior, but we are integrating with respect to theta. Okay, so you have to do more calculation for that. But if you recognize, okay, so I know this is normal distribution, it is gamma distribution, then you have to add this constant part, proportional part, by yourself without calculating it. Okay, so let's write the likelihood function xi and then the prior distribution. So here alpha beta are constant parameters. Okay, so these are fixed quantities. They are also not known. But our main unknown parameter is here theta minus theta beta. Okay, so let's try to get rid of this constant part also. Okay, so try to write everything in terms of theta. Okay, and combine some parts. So we have theta here, theta here. So we have theta and plus alpha minus 1. Okay, and e to the minus theta summation xi plus beta. Okay, so this is the proportional part. So now at this point you have to look, okay, look at the form of the PDF. So theta is a random variable, okay, don't forget that one. X not here. We are trying to estimate theta using Bayesian approach and using the distribution of theta. Okay, so here when you look at this, can you recognize one known distribution here? You should. And as you guess, yes, it is gamma, because if you remember the form of gamma distribution, which is x to the alpha minus 1 e to the minus x over beta, right? The not constant part, but the main part with the random variable. So instead of x we have theta, instead of alpha we have m plus alpha, okay, and then instead of x we have theta here, and instead of 1 over beta term we have 1 over this term. Okay, so basically we can say that our theta posterior will be gamma, okay, with parameters m plus alpha and 1 over summation xi plus beta. Okay, so this will be the posterior distribution. If you cannot recognize this distribution as gamma, you cannot use this proportional approach. You have to calculate the integral of this quantity, this whole quantity, with respect to theta. Okay, integrate it with respect to theta, and then find the constant parts of the gamma distribution after that calculation. And also we have, remember, so this part also. So it will be hard, kind of mathematical calculationally time consuming, let's say. It's not hard, but if you use this approach it's much more easy to get the results. And from here actually, so we started with gamma for the prior distribution, but we update the parameters of gamma distribution after collecting our sample. So previously our prior distribution was gamma, our parameters was alpha and 1 over beta, but right now we have gamma m plus alpha, which is the sample size. Also we add beta to summation xi term. So this is the updated version of the parameters. So from here basically if you want you can write the PDF given x1 to xn, which is our beta parameter to the alpha n plus alpha and gamma n plus alpha, theta to the n plus alpha minus 1 e to the minus theta summation xi plus beta. Our theta is positive and beta are positive. And if you want to find the expectation of this posterior distribution, then we will have conditional expectation of theta given the sample random variables. All we have to do basically obtain the expectation of gamma distribution, which is the multiplication of these two parameters, m plus alpha over summation xi plus beta. Okay, so this can be used as a point estimate of the unknown parameter theta, but we will discuss that concept later in these notes. Bayesian point estimate of theta. Okay, so instead of using MLE of theta maybe for the estimate of theta, we can use this, but as you can see we have some unknowns alpha and beta still here. Also, if we want to write this quantity in another form, so we will get alpha over, if we write summation xi as y, so we will have this quantity plus n beta plus y. And if we write it this way, alpha over beta and 1 plus y over beta plus n over y. You don't have to do this actually, but I have a point. So we have 1 plus y over beta alpha beta, which is the mean of the prior distribution, remember, plus 1 over 1 plus beta over y and n over y. And this was the MLE. Remember, MLE of theta. So basically, if you look at the Bayesian point estimate or the expectation of the posterior distribution, what we are getting is the weighted average of mean of prior. And we have the MLE of theta, right? So these will be we have the weighted average of the sample mean of the prior, and also the MLE of theta. So this will give us the weighted average of the mean of prior distribution and MLE of theta. So if you focus on the parts basically, so when sample size goes to infinity, when n goes to infinity, we expect that this part goes to 0. Okay, and when n goes to infinity, we want that this part goes to 1. Okay, so when sample size gets larger and larger, this quantity converges to the MLE of theta. So when we have a large sample sizes, basically this point estimate or the expectation of the posterior distribution converges to the MLE of theta for this example. So this is not always the case, but we have this in this case. Okay, so in this Bayesian concept we have also another thing. It's actually kind of mathematically creates ease. We have some conjugate family of priors. So when we have a certain prior distribution and the distribution for the sample, then posterior distribution should be same as the beta. Not beta, prior distribution with different parameters. So if the prior distribution is gamma, like in this example, then posterior distribution will be gamma also. Or when the prior distribution is beta, then posterior distribution also beta with different parameters. So if this is the case, this family of distributions known as conjugate family of prior distributions. So whatever the prior distribution, we have the same posterior distribution with different parameters. Okay, so conjugate family of prior distributions. Okay, so we have another family, as you can see, family of distribution. So a family of prior distributions leading to the same family of posterior distributions for samples from a given distribution. Okay, so if the sample distribution is, for example, Bernoulli with parameter theta, And if the prior distribution is beta parameter with these alpha and beta parameters, so we know that our posterior distribution will be also beta distribution with different alpha and beta parameters. Similarly, when our distribution, sample distribution is Poisson for theta, then we have gamma prior, then our posterior will be gamma also with different parameters. Okay, so let's look at another example. Let's say we have a sample from the Bernoulli with parameter p, and we have a random sample, and we want to estimate the parameter p here, let's say, but we want to use Bayesian approach, not the classical approach. Okay, so we know that y summation xi is binomial distributed for a random sample, and here assume p is unknown and must be estimated. Okay, and here we assume that the prior distribution on p is beta, alpha, and beta. Okay, so this is appropriate distribution for p. Why? Because if you look at the range of p here, it is between 0 and 1. And what is the range of beta distribution for p? It's also 0 and 1. So the range of p's should coincide basically. So it is a proper prior distribution for p. Okay, so appropriate choice for as a prior distribution. Okay, then let's write the PDF of the prior. Okay, so we have alpha, beta, p to the alpha minus 1, 1 minus p to the beta minus 1. Alpha and beta is positive. And when we consider the likelihood function of x1 to xn given p, so this is p to the n, 1 minus p to the n minus y, and y taking values from 1 to n. Okay, then our posterior distribution then can be calculated again using the proportional approach. It's easily, which is the multiplication of the likelihood function times the prior. Okay, so that's that easy actually. If you don't want to use this approach, use equality and write the same thing here, and you have to integrate the same thing for p. Okay, L H P. Okay, so we don't want to do this calculation and use proportional approach. Okay, so then let's write the prior or likelihood. I started with the prior. Alpha minus 1, 1 minus b, and minus, 1 beta minus 1, and then we have the distribution for the likelihood 1 minus b to the n minus y. Again, get rid of this constant part and combine the things with p, alpha plus y minus 1, and we have n minus y plus beta. Okay, so now from at this point you have to recognize this distribution. But actually, if you look at the first part, and if you know the conjugate family thing, then if the prior is beta, then we will end up with beta. And also when you look at the beta PDF, so we have without the constant part, let's just focus on this part. So we have p to the parameter minus 1 and 1 minus p to the parameter minus 1. So we have the same thing here. So we have the parameter, we have the p, and we have the parameter minus 1, which is the where the parameter is this one, okay, and then we have 1 minus p to the parameter this, okay. So these are proportional actually, okay. Then we can easily define the distribution, posterior distribution, as beta with parameters y plus alpha and n minus y plus beta, okay. So this will be the posterior distribution, and if you want we can get the expectation of the posterior distribution. I use theta here, but it should be p, sorry about that. So then we can find the conditional expectation, or just the expectation of the posterior distribution. So if you know the beta expectation, you can easily get it actually. Y plus alpha plus n plus beta minus y, and we will have y plus alpha n plus alpha plus beta, okay. So this can be the Bayes estimator of p, okay. So we can use as an estimator for p. Okay, if we ignore basically the Bayesian approach, maybe we can use just x bar, from Bernoulli distribution. It's the best estimator for minimum variance unbiased estimator for p, right? Sample mean. Again, if you you can get some little calculation, and you can also show that again this can be written as a weighted average of the MLE of p and also the mean of the prior distribution. But I will not give it, so we will have a convex combination of the MLE of p and also the mean of the prior distribution. Okay, so let's see. Okay, so let me stop here. So I will continue with the loss and risk functions, and also the confidence interval and testing procedures in the next note. Okay.